In this video we're going to look at a number of the probability laws. If you see the learning objectives, we're going to look at mutually exclusive, exhaustive, look at some laws around that, and then independence and a law around that. So that's what we're looking at in this video. Now we've first of all got a Venn diagram here, and these two events are mutually exclusive because they cannot happen at the same time. People might say, oh, I can understand them a bit, but you either understand them or you don't understand them yet. So they should really say don't understand Venn diagrams yet, if we're going to be like growth mindset. Okay, people understand Venn diagrams, people who don't understand Venn diagrams yet. A classic example would be the idea of Marmite. You either love it or hate it. You don't love and hate it. They are mutually exclusive. They can't happen at the same time. So let's get down a definition of mutually exclusive events. So our definition is events are mutually exclusive if they cannot happen at the same time. And there's a formula around this which is called the addition rule for mutually exclusive events. Looking at our diagram, if I wanted to know the probability that either people understand Venn diagrams or don't understand Venn diagrams, let's say the probability of being one of the people who understands Venn diagrams was 0.3 and not yet was 0.7. Well, if I wanted the probability of understand or not understanding, well, because there's no intersection here, I would literally just add 0.3 plus 0.7, which is 1. It won't always sum to 1, but if they do sum to 1, if they do add up to 1, it means that these two events are also exhaustive. They cover every possible option, but we'll get on to exhaustive in a second. Just to come back to that formula. So this formula works if these two events are mutually exclusive. All right, well, sometimes, like with these two, they're not only mutually exclusive, they're also exhaustive. What exhaustive means is that there are no other options than the ones spoken about. The set of events is exhaustive if the set contains all possible outcomes. All possible outcomes. So with Venn diagrams, you either understand them or you don't understand them yet. There are no other options, so these two are exhaustive. Okay, you either love Marmite or you hate it, no other options. Although that's not really true, you could okay it, so they're not really exhaustive. Now for being exhaustive, sometimes some examples helps us get our head around it a little bit more, so I'm just going to show you a few different visual examples. This diagram shows more than two mutually exclusive events, which are also exhaustive. So if you go into a Walmart, it's a shop, and then you want to pay, there's a number of options, and Walmart have said they can only have 4 options. You can either pay everything by credit card, everything by debit card, everything by cash, or everything by cheque. You can't use a combination, you have to do just one. Now these are mutually exclusive because you're not allowed to pay by more than one, and they're exhaustive because they're the only options you can pay by. So these are both mutually exclusive and exhaustive. And if I added up all these probabilities, they would have to total 1 because they fill up every single part of the space, and that will be true for a set of mutually exclusive exhaustive events. The sum of all probabilities will always be 1. Now we're going to work through a worked example. So Josh is playing a fairground game and he can win a prize. So he throws a dart at a playing card which is on a revolving wheel, and he can either win £10 if he hits an ace or a cuddly toy for a picture card, bearing in mind that there are only 4 aces in the whole pack, but there are 3 picture cards per suit, so you've got 12 picture cards, so it's much more likely. So we've got 2 different events. We've got event A, and if you notice we've defined these events. So event A is Josh's dart hitting an ace. So if they just tell you these without naming events, it's good for you to define them. So event A is Josh's dart hits an ace, and the probability of A is 0.02. B, Josh's dart hits a picture card, 0.08. So what is the probability of Josh winning a prize? Now, since picture cards and aces are never the same, these two events are mutually exclusive. Josh cannot hit a picture card and an ace at the same time. Now, they're not exhaustive because there are lots of other things that he could hit, a 3, a 7, etc. But these are mutually exclusive, and because they are mutually exclusive, we can use the formula, which is the addition rule for mutually exclusive events. So the probability of Josh winning a prize is the probability of hitting an ace or a picture card, and so we write it like this, which is 0.02 plus 0.08, which is 0.1. And that is using our formula, the addition rule for mutually exclusive events. Now for part B, we want the probability that he doesn't win a prize. Okay? Well, if he does win a prize 0.1 times, he won't win a prize the rest of the times. So it's 1 minus 0.1, which is 0.9. A, B, because this is the rest of the times. The rest of times. So this is when he wins. And also if you want does not, then you're going to do 1 minus the event. Now next we're going to extend what we know to the general addition law, and this is when true even if events aren't mutually exclusive. So this first diagram shows the probability of A union with B. Okay, so it could be A or B. So you could have it as A or B. So the probability of A or B. So it could be anything in A, anything on B. Well, how would we calculate that? Well, the problem is, if we just had all of A and added all of B, if you notice, A includes this part and B includes this part. So what you're actually going to be left with is not only that part, but also an extra of the middle. You're going to have an extra one of those. So if you just wanted what's in this diagram, you're going to have to take away that part. So we have our general addition law. And this funny N-looking shape here means intersect, the intersection here. And this is your formula that you should now have in your notes. And then we're going to look at another worked example. Okay, so we've got another pack of playing cards, and we've got red and picture cards is what we're interested in. Now notice these two are not mutually exclusive. Some picture cards are red and some red cards are picture cards, so you cannot use the mutually exclusive rule. We have to use the general addition rule, okay, which is the one in blue at the top of the screen. So we're going to use that. In this case though, it's going to be, so R is the event that the card is red. The probability a card would be red. Well, out of a pack of 52, half of them are red, that's 26. The probability it's a picture card, well, there are 3 picture cards, Jack, Queen and King per pack, per suit, and there are 4 suits, so we've got 12 picture cards. And then we need to get rid of the red and picture cards. Well, as we said, 3 per suit, 2 red suits, so we need to take away 6 52s. Okay, if we just work that out, we should get 32 out of 52, which you can simplify if you wish. Okay, so that's our complete answer. Make sure you read the question really carefully. Q is a picture card, not just a queen, and probability, you are expected to know things like decks of cards. So if you don't know them yet, then start playing more card games with your friends. Looking back at our learning objectives, we've looked at mutually exclusive and exhaustive, and the addition law when they're mutually exclusive, and we've looked at the general addition law for when they're not mutually exclusive. but we now need to look at independence, what it means, and using the multiplication rule. Now this is actually something that is in GCSE maths, but I'm just going to recap it so we know what we're doing. So independent events are said to be independent of each other if one does not depend on the other. In other words, one does not affect the other. Now sometimes people can open these to interpretation and say, well, if it rains on one day, it's more likely to rain the next day because it's winter or whatever, but we're often assuming two events are independent. And it's very useful to do that because there is a multiplication law for independent events, which basically just is this. In other words, probability of A and B both happening is probability A times probability of B, and you've probably seen them as most commonly on a tree diagram, where if you wanted to have this one and this one, you always multiply. If that was 0.8, 0.2, the probability here would be 0.16 because you would multiply them together, and that's probably where you've most likely seen this before. And you know from tree diagram most probably is that if I had an extra branch here and an extra bit there, 0.1, that would be then 0.016 because you'd multiply them all together. So this can be extended to probability of A and B, and C is probability A multiplied by probability B multiplied by probability of C. But this only works with independent events. We're just going to look at one worked example. Okay, so this is how it could be worded for you. Helen likes music. The probability that her grandmother buys her a CD for her birthday is 0.7 and her mother is 0.5. What is the probability she gets the CD as a present from both her mother and her grandmother? Now notice this thing in brackets here. Assume that they do not discuss what they are going to buy for Helen for her birthday. This is important because if they do discuss, they'll then become dependent on each other. The mother might think, oh, the grandmother's buying a CD, I won't, etc. Whereas if they don't discuss it, these can be considered as independent. So we assume that these are independent. And because we assume that they're independent, we can use the independent multiplication law, which basically just means we can multiply these together. So 0.5 multiplied by 0.7 equals 0.35. Really important in your notes to comment how this means we're assuming they're independent, and that is why we're allowed to multiply them. You might even want to write out the formula again to say that is why you're multiplying them, but you might be quite used to that from GCSE maths. But just really here, this assumption is we're assuming that they are independent events. Okay, we have now covered everything on our learning objectives, so you're going to have to go at practicing these skills with your practice questions.